motion. Now today I like to discuss the molecular motion in two-dimensional whenever the molecules are in planar motions or in two-dimensional motions. And you know practically all we are whenever moving on the earth, it is actually the planar motions, and z component of our motion is equal to 0. Only the birds can move in a three-dimensional motions when they fly. So the molecules here also having the three-dimensional motions, but we like to see what will happen whenever the molecules are moving in 2D motions or in planar motions. Suppose this is the x-axis. This is the x-axis, and this one is y-axis. And this is origin. Let us consider the molecule moving along the x-axis with this velocity u. And suppose this one is u. U the velocity, the x component velocity of the molecules along this x-axis. And this one, suppose u plus du. Du is the small range. Du is the small range. And we have also already considered whenever the molecules or fraction of the molecules or probability of a molecule to have the x component velocity u within the range du, it is denoted by pu, and pu equal to dnu by n, and this is the function of u and the range du. dnu is the number of molecules. dnu is the number of molecules that are having this x component velocity u within the range du. And whenever this dnu is divided by n, it will give you the fraction of the molecules, or you can say it is the probability of a molecule. This is the favorable event or favorable molecules, and this is the total molecules. So favorable molecules divided by total molecules, this ratio will give you the probability of a molecule to have the x component velocity u to u plus tu. And already we have decided this fu, it is called this x component velocity distribution function. Fu is equal to the x component velocity distribution function, and it is already derived. It is a into e to the power minus b u, as fu is exponential nature of this velocity, and this fu will not contain u, must not contain u, but may contain u square. And a and b, these are the constants independent of u, but they will depend on the nature of this gas and the temperature. And you see it is the fraction. Whenever du is equal to 0, then fu is the fraction of the molecules having the x component velocity u. So here this is U, and this breadth is du. So the number of molecules or the fraction of the molecules those are having the velocity u to u plus du could be located within this area, in this velocity space within this area. And all these molecules have the velocity u to u plus du. They will be located within this area. And in a similar way, if we consider this is u and this is u plus this is v and this is v plus dv. If we consider the molecules are having the velocity v along this y-axis, and this is origin. Here actually 0 to plus infinity, here 0 to minus infinity, 0 to plus infinity, 0 to minus infinity. This is the range of u and v. So actually the molecules that the probability of these molecules having the velocity v to v plus dv will give you this dnv and divided by n, and this is equal to fv into dv, and fv is again the y component velocity distribution function, and dv is the range. So here also fv equal to a into e to the power minus b square. A and b are constant. In both the cases will be the same. As the molecules are having the same probability along this x-axis and along this y-axis, so the mathematical format of this function will be the same. Here only contain this function will contain u, and here the function contain v. This is the difference. And I have also told already that this must not contain u, but may contain u square. As the probability of this molecule to move 0 to plus infinity is identical with these molecules moving along the x-axis with the range 0 to minus infinity. So in order to having the equal probability, this velocity must be squared up. So when the molecules that are found, or the fraction of molecules that are found within this area having this speed, having the velocity v to v plus dv, will also found in this way. So if we consider the molecules moving x-axis and one molecules are moving in x-axis and also in y-axis, then the probability uv will be equal to the product of these two probabilities. As we have seen, the probability is a multiplicative property. So it will be p u and into p v. So if we write here, then this will be equal to n and uv divided by n dn. dn uv divided by n equal to these two values are, or it will be f du and into fv into dv. So if we set the value of the functions, then this one is a square, and the exponential term minus b and u square plus v square, and here du and dv. It is the du. This one is du and this one is dv. So here the probability of the molecules, probability of a molecule to have the x component velocity u to u plus du and y component velocity v to v plus dv, this fraction of molecules will be located within this area, within this rectangular area in a planar motions. Whenever x-axis and y molecules are moving along this x-axis and y-axis, it is the planar motions. Z component of the velocity is equal to 0. So we have already shown you that, and this is the number of molecules having the velocity u to u plus du and v to v plus dv, and n is the total number of molecules. So this fraction of the molecules to be located within this small area bounded by du and dv. One side is du, another side is dv. So this is the area. So if we put the value a, we have already seen, equal to m by 2 pi kt to the power half, and b equal to m by 2 kt. If we put here, then actually the distribution function p uv equal to d n uv divided by n equal to, it is square up, so half root will be wiped out, so m by 2 pi kt to the power 1 and e to the power minus, and this u square by v square. This is the u and this is v, and this is the resultant speed c, resultant value. So actually c u square plus v square equal to c square. C the resultant speed, and this speed can move in all directions within this plane. So this is the speed. So here actually a square, or you can write minus m by 2 kt, mc square by 2 kt, and here du and dv, and this is the polar coordinate. See the polar coordinate, and u and v, these are the Cartesian coordinate in velocity space. So if we evaluate this area, this area could be evaluated in different ways. By putting the polar coordinates, these two, we know in position space dx dy equal to r dr and d phi. You know phi is the azimuthal angle whose range is 0 to 2 pi, and r the radial distance. This is phi. So in velocity space, this du will be replaced by du, and dx will be replaced by du, dy replaced by dv, and this is equal to radial distance is replaced by c. So c and dc and d phi. If we consider, if we wave out, if we remove the restrictions of d phi, means not within this small d phi, then d phi to be integrated within the full range. So in this case, dn, c and phi divided by n equal to m by 2 pi kt, and here e to the power minus mc square by twice kt, and in this case is c, dc and d phi. If we remove the restriction for the movement of the molecules along a particular range of this azimuthal angle, and we consider the molecules can move freely in all directions on a plane only having the magnitude c to c plus dc, no restrictions of this phi. So d phi to be eliminated. So when d phi to be integrated within this full range. So in that case, dnc by n, this is equal to m by 2 pi kt, and here e to the power minus mc square by twice kt, and here c dc, and it is the 0 to 2 pi. 0 to 2 pi is the range of the azimuthal angle, and here it is d phi. When d phi is integrated, it will give you phi, and the range is 0 to 2 pi. So this integration will have this value 2 pi, and this 2 pi, this value will give you the value of 2 pi, and this 2 pi and this 2 pi, this integration will have the value 2 pi, and this 2 pi and here 2 pi will be cancelled out. So it will be, so dnc by n, probability of a molecule to have this speed, not velocity, speed c to c plus dc is equal to m by 2 pi kt, and e to the power minus mc square by twice kt, and here 2 pi will be cancelled, here only kt, and it is c dc. T the temperature, m the molecular mass. So this distribution, this speed distribution depends on the temperature and the molecular mass of this gas. And you see the it is the planar motions. So this value also could be evaluated in an alternative way in polar coordinates, when the molecules on a plane can move in all directions. Then in polar coordinates, actually this area, this is origin, and you can write a circle of radius c. In a velocity space, it is the speed. U and V having a particular directions, U along this x-axis, V along the y-axis, but C has no direction. C can move in all directions with equal probability. So it is expressed by a circle in planar motion. If we consider the number of molecules or fraction of the molecules having the speed c to c plus dc, irrespective of direction on the planar motions, then we can draw another circle whose range is dc. This is c and this radius is c plus dc. So the width of these two circles, concentric circles, is dc. So this area in polar coordinates, this area will give you the value, this is the circumference is twice pi c, circumference into the breadth will give you this area into this dc. So actually twice pi c dc is the area including the two circles, and this the molecules that have this speed c to c plus dc irrespective of this directions in a planar motions will be placed, or points would be shown in this area. And you know, in here it is the area, this one, and here this area is this one. So du dv, you can write twice pi c dc. So whenever 2 pi is written, 2 pi cancels, and in this case we put here 2 pi c dc, and this formula is coming up. In this way also we can evaluate du dv. So this is the Maxwell distribution of molecules along this planar motion, on the planar motions. Whenever all the molecules are moving in two-dimensional motions, means a planar motion. And you see from this, if you draw this curve, and this could be written as fc dc, where fc is called speed distribution function. Speed distribution function, of course, in planar motion, and this is equal to m by kt and e to the power minus mc square by twice kt, and here c. dc is cancelled. So this is this speed distribution function. If we plot the speed distribution function, c is having the range 0 to infinity. C will never be negative value, and this is why this function contains c, no problem. So here here c and here fc. It is origin. So fc versus plot, fc is plotted against c, as we have done in earlier cases. So when c equal to 0, here single component is there, c not c square. Okay, as c will never be negative. So whenever c will be equal to 0, then fc also equal to 0. So this curve will start from this origin. So this curve will start from the origin. And here the two terms. Here c, this is the non-exponential term. And this one is exponential term. Exponential term. So whenever the velocity or whenever the speed is low, this non-exponential term will dominate. And when c is having a larger value, this exponential term will play the dominant role. Okay? Then you see, unlike the 3D motions, as you have seen earlier, here in the case of two-dimensional motions, here it is not c square but it is c. In case of 3D motions, this non-exponential term contains c square, and here also c square. But in 2D motions, in planar motions, it is c but it is c square. So for a gas at a given temperature, m and t, these are constants. So fc versus c, whenever we plot this non-exponential at the low value of c, this exponential term will be dominant, and when c is increased, this term will increase. This term will increase this value of fc. So this, but in a lesser extent, this curve will rise with the increase of c, but at a slower rate. Slowly it will increase. So it will slowly increase. Slowly increase. But when this c is having higher value, this exponential term will dominate, and exponential term will, as c square is there, m to kt, these are constants, and it is trying to decrease. C is large, so c square is very large. So the effect of exponential term is much more dominant over the value of c. So this, when this value will try to decrease this value of fc. So with the increase of c at higher value of c, this curve will fall very steeply. So what will be the nature of this curve? How this curve looks like? It will start from fc versus c plot. Will start from origin. It will increase slowly, or it will rise slowly, but it falls very rapidly and becomes asymptotic. Means when c is equal to infinity, then fc equal. C when equal to infinity, then this one equal to 0, and 0 into all these things will be also equal to 0. So this will be the nature of this curve. This difference of this curve is due to here these two terms, here contains c, but here contains c square, and c is very large. C square is again very, very large. So this exponential term will decrease very sharply, will decrease the curve very sharply after attaining this peak. And naturally you can see, and this is the maximum, and this one is CMP, means most probable speed in 2 dimensions, of the molecules. So if we like to find an expressions of CMP, then we have to and this is Gaussian distribution. One term is increasing, other term is decreasing, so it is exponential. It is the Gaussian distribution curve. So if we like to find the expression of CMP, then we shall have to take the help of this differential calculus maxima minima. So maxima minima this is the case dFc divided by dC equal to 0. If we put this value of Fc here and differentiate with respect to C, then or you can write m by kT will remain as it is constant, and here the d by dC and within third bracket e to the power minus mc square by 2 kT into C, and this is equal to 0. Or you can see this m by kT, and this is the product of two variables, and it is differentiating with respect to C. M and kT, these are constants. So this has been kept constant, e to the power minus mc square by twice kT, and C is differentiated with respect to C, and this is equal to 1, and plus now C is kept constant and this is differentiated with respect to C. So e to the power minus mc square by twice kT, and this one when differentiated with respect to C, this will be minus twice mc divided by twice kT bracket close, third bracket close, equal to 0. So 2 cancels. So if we solve this one, then m by kT or and e to the power minus mc square by twice kT, this is common, and here 1 minus, here minus, 2 cancels, C and C square, then mc square by kT and equal to 0, m by mc square. But when this will never be 0, m by kT will never be 0, this is constant term. So this may be 0 or this may be 0. When this one equal to 0, e to the power minus mc square by twice kT equal to 0, then C tends to infinity. When C tends to infinity, this curve will give you the minimum value. So this one is rejected. When then another term, this may also be equal to 0, and this will correspond to the maximum value of this Fc. So it is 1 minus mc square by kT equal to 0, and this C corresponds to CMP. So C equal to root over of kT by kT by m. Root over kT by m. Root over kT by m. So this will correspond to the maximum value of Fc. So this C we can write Cmp, and this is equal to root over of kT by m, or you can write RT by m, capital molar mass. So by this way you can calculate this Rn mean most probable speed of the molecules in planar motions at a given temperature T, and for a given gas whose molar mass is known to us. And similarly, if we find the expressions of this C bar is the average speed of the molecules in planar motions, then according to formulation, C bar equal to 0 to infinity. C is having the range 0 to infinity, and here C and Fc into dc. If we put this value of Fc here, then it will be m by kT. Will go outside of the integration, and 0 to infinity, and here C, and here C means C square, and e to the power minus mc square by twice kT and dc. Okay, here we will write Fc equal to m by kT and e to the power minus mc square by twice kT into C. Now we are going to calculate this average speed. So m by kT, and here this integration you can solve by the use of this gamma function. Here it is the expressions of this gamma function to evaluate the standard integrals. Here n equal to 2. So it will be gamma 2 plus 1, 3 by 2, and divided by 2 into m by 2 kT and to the power 3 by 2. And gamma 3 by 2 equal to gamma half into gamma half equal to half, and gamma half equal to root over pi. So it is root over pi. So this is again equal to m by kT, and here half and half, 1 by 4, and here root over pi, and this is taken upper numerator, so twice kT by m into 3 by 2. So to simplify this one, it is better to take all the terms under the umbrella of square root. Then I think it will be very easier to get the final value. So this one equal to root over, here whenever root over is taken, it is m square, here kT square, and here 1 by 40, and here pi, and here 8 kT 3 divided by m 3. it becomes easier to cancel the like terms. This one 3 by 2, whenever root over is taken, then 2 kt by m cube. 2 kt by m 2 cube means 8 and kt to the power 3, and here it is m to the power. Now you see m square 1 m remains and kt 1 kt is there, and this one 2. So this will be equal to root over of pi kt by m. This is the average speed of the molecules moving in a planar motions. So here also we can write c bar equal to root over of pi kt by m, or you can write pi rt by capital M, molar mass. It is the molecular mass, it is the molar mass. Then our task is to find the expressions of CRNS. CRNS means root over of c square bar, root mean square speed. Close. First we find the mean square speed. Mean square speed is c square bar, and this is equal to 0 to infinity, and here c square and fc and bc. And if we put the value of fc here, then this will be equal to m by kt will go outside of this integration, 0 to infinity. Here c square and here c means c cube, to the power minus m by mc square by twice kt, 2 kt into this. C square is the power minus mc square by 2 kt into c. Again, this integral, value of this integral could be obtained from this use of this gamma function. So this is why I have taught this gamma function first, to get this evaluation of the standard integrals. And if you here m equal to 3, so this is equal to m by kt, and it is the gamma. 3 plus 1 means 4 by 2 means 2, and here 2 and m by twice kt square, b square means b square, b here m by 2 kt, and root gamma 2 and gamma 2 equal to 1. Gamma 2 equal to 1, so m by kt, and in this case half into 2 kt by m square, and this is equal to 1 m will cancel, and this 2 and 2 kt will be there, so it will be 2 kt, 1 2 is cancelled, 2 kt by m, 2 kt by m 1 m remains here, and kt 1 kt remains there, and it is 4, 2 square means 4 by 2 means 2. So c square bar root over root mean square speed, RMS, and this is equal to root over of twice kt by m, and this is equal to 2 rt by capital M. So for a gas, suppose oxygen at a temperature 300 Kelvin, you can calculate all these three values, and you may compare. And if we compare here, CMP is to C bar is to c square bar root over this one equal to root over of kT by m is to root over pi kT by it is equal to 2. 2 will be there. 2 will be there. In some calculations, some mistakes may be mistaken. Here 2 will be coming. Here also 2 will be coming. So it is twice n and is to here root over of twice kT by m. So naturally you can see CMP is less than C bar and less than C square upon root over. This is the highest value, this is the lowest value. This kT by m, kT by m, kT by m are common. So this ratio you can write 1 is to root over of pi by 2 is to root over of 2. And this one 1 is to, this is 1 is to 1.25, 1.253 is to 1.4144. So if you, from this ratio, if you know the value of a gas at a given temperature, any one of these three, then other two you can calculate by the use of this ratio. Now we are coming, so if we put these three average speeds in this FC versus C diagram, then this is the lowest value and here it is the C bar and here it is C square bar 2. These are the place of the average, three average speeds in FC versus C diagram. Now we are coming to the kinetic energy distribution of the molecules in 2D motions. Kinetic energy distribution. Of course, Maxwell kinetic energy distribution of molecules in 2D motions, in planar motions. Planar motions. Planar motions is very very easy to understand in comparison to the 2D motions. So it is planar motions. Epsilon kinetic energy of a molecule equal to half m c square. This is the kinetic energy of the molecule, and c the speed of the molecules and m the molecular mass. So d epsilon equal to half m into twice c and dc. 2 cancels. So mc dc. If we write here dnc by n equal to m by kt and to the power minus mc square by twice kt and here c is. So whenever we are converting this speed distribution into kinetic energy distribution, then it will be dn epsilon by n equal to m by k, actually mc dc. mc dc will give you the d epsilon. So here m by 1 by kt to the power minus mc square by half, mc square by half equal to epsilon. So epsilon by kt and d epsilon only. This is the kinetic energy distribution. This is the fraction of the molecules having the kinetic energy epsilon to epsilon plus d epsilon. And from this you can also calculate this average kinetic value. Average kinetic value in two-dimensional motions. It will be equal to 0 to infinity, and here epsilon, and here dn epsilon by a. If you put this value, integrate, and use this limit, then it will be equal to a. You can do by yourself. Now one thing. So this one equal to dnc by n equal to m by kt. dn epsilon by n equal to 1 by kt to the power minus epsilon by kt and d epsilon. This is the kinetic energy distribution of the molecules in planar motions. Epsilon is the kinetic energy of a molecule, d epsilon the range, and k and t. Surprisingly, it is also seen that this kinetic energy distribution, molecular mass is totally absent. Means nature of the gas is no longer here. Means kinetic energy distribution does not depend on the nature of this gas. It will depend only on the temperature. So at a given temperature, all the gases will have the same distribution curve irrespective of their nature. Nitrogen, oxygen, hydrogen, carbon dioxide, all the gases will have the same distribution curve. Kinetic energy distribution curve, M is absent. Now one thing I like to deduce the fraction of the molecules having kinetic energy greater than or equal to epsilon 1 at a temperature T. This is very important, especially in the case of reaction kinetics. And I will show what will be the fraction of the molecules. Whenever the fraction is multiplied by the total number of molecules, it will give you the number of molecules having the kinetic energy greater than or equal to epsilon 1 at a given temperature T. So in this case, epsilon 1 by 2 infinity. This is the lower value. This is the lower value. So here d n epsilon by n equal to, you can write this n epsilon 1 by n. It is the fraction of the molecules having the kinetic energy greater than or equal to epsilon 1 at a temperature T. And this could be shown 1 by kt common, and this is integration. Epsilon 1 is the lower limit and her limit is infinity, and here it is e to the power minus epsilon by kt and d epsilon. So this one equal to 1 by kt, and here whenever this one is being integrated, then e to the power minus epsilon by kt and divided by minus 1 by kt, and the range is epsilon 1 to infinity. And so this 1 by kt and this 1 by kt will cancel, and if you omit this minus, then limit will be changed upside down. So e to the power minus epsilon by kt, and here it is infinity, here is epsilon 1. And this one actually, first limit e to the power minus epsilon 1 by kt, and when infinity is placed here, it is equal to 0. So it is minus 0. So this is equal to minus epsilon 1 by kt. expression becomes very, very simple in comparison to the 3D motions. In case of 3D motions, the calculations was very difficult. Here calculation is very simple. So this fraction n epsilon 1 by n equal to e to the power minus epsilon 1 by n. If this epsilon is expressed in kinetic energy per mole, then it will be Ne1 by n equal to e to the power minus E1 by RT. Avogadro number is multiplied in numerator and also denominator, and this will be the expressions. Whenever E1 is expressed in terms of the energy per mole, kinetic energy per mole. This is important in the sense that in kinetics of chemical reactions, the mechanism of this, how the reaction occurs, then one thing is first molecule collide. Collision is the precondition for the molecules to react. So molecules are colliding first. And whenever we are considering the two-body collisions, this is a molecule coming here, and this is another molecule moving in this way. So these molecules are colliding. Whenever these molecules are colliding, then this can be taken as the plane. These molecules are in planar motions. Suppose one molecule is coming here and another molecule is coming here. So this is the plane in which the binary collisions or two-body collisions occur. And two-body collisions or binary collisions is very, very common. In most of the chemical reactions, the molecules undergo the binary collisions. Ternary or three-body collisions are rare, are very rare. And four-body collisions is impossible. You can see in the state, two persons may collide. But if you see three persons, here one person, here one person, here one person, three body collisions at the same time on the state, three persons colliding, three persons giving a thrust at the same time, it is very, very rare. If you can see, you are much more lucky. But four persons are colliding at the same time, it is impossible, not possible at all. So we are considering the two-body collisions. So molecules are colliding, two-body collisions, but all the molecules, those are undergoing the binary collisions, will not react. Only those molecules can react whose energy will exceed a certain critical minimum value, and this critical minimum value is called the activation energy of the molecules. So only those molecules will undergo the reactions who can acquire the excess energy greater than or equal to the activation energy. So epsilon E1 may be taken as the activation energy per mole. So by this formula you can calculate at a given temperature, how many fraction of the molecules will acquire the activation energy. We can write one problem. We can show also one problem. Calculate percent of molecules greater than or equal to 500 joule mole inverse at 27 degree centigrade. So if we calculate NE1 by N equal to e to the power minus here 500 joule mole inverse and divided by 8 R, the value of R is 8.31 joule mole inverse Kelvin inverse, and the temperature is 27 degrees centigrade, means 300 Kelvin. So this is equal to joule, mole inverse, Kelvin inverse, Kelvin, all will cancel, and this value will come out 0.8. This is the fraction, or this is the probability of the molecules to have the kinetic energy greater than or equal to 500 joule mole inverse at a temperature 27 degrees centigrade. If you multiply by 100, then it will be 82%. Means if you have, for example, 100 molecules in your vessel at a 300 Kelvin temperature, then 82 molecules will acquire this energy. If this one is the activation energy, then all these molecules will undergo the chemical reactions at this temperature. So this is all about my today's lecture, and by this lecture we have completed the kinetic theory, Maxwell's distribution of Maxwell distribution of the speed. First, we have done some problems, coordinate systems, interconversions, and the gamma functions, concept of probability. Then 3D Maxwell's distribution law in 3D motions, then 1D motions. Then lastly, I discussed this 2D motions of the molecules, means whenever the molecules are moving in a planar motions. So I think this lecture will be helpful to some extent, at least, especially for the chemistry students or net get experience or IT jam experience. So I hope if you like this video lecture, then please subscribe. It will boost up for doing more videos for your benefit. Thank you all for watching this video.